Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So again, we going to continue regarding our handout number 3. So today's session, I'd like to focus on solving maybe one of two examples taken from this handout. I'm still not referring to any problem from our textbook because I presume some of you still couldn't access to the textbook. So therefore, I'd like to discuss problem taken from the handout because I have already uploaded all this problem in our e-learning for you to download. Okay, so today I'm going to continue solving a problem from the handout. So let's focus on the second question. Remember, this exercise focus on the issue that we are currently discussing, which relate to the sources of electrostatic field, and we already know that the main characteristic of the sources is they are stationary, meaning they're not moving, and we have model 4 types, which are the first one, we call it to be point charge. The second is known as line charge. Third, surface charge, and the final one should be volume charge. We have done example regarding line charge. So that's in our question number 1. So now we would like to continue with the third model, which is the surface charge. So let's focus on question number 2. Okay, so let's read the question together. It states here, a circular disc, okay, of radius A has a surface charge density that increases linearly away from the center and is given as rho s, and we know rho s is known as surface charge density and is equal to Kr, where K here is assumed to be constant parameter. So the question asks us to do what here? To determine the total charge on the disk. Okay, so that should be what we ask to solve here. So question number 2 now. Okay, question number 2. Okay, usually when I want to solve this type of problem or EMT problem, I like to draw. That's what usually my first step when solving a problem. I always like to visualize what should be our problem here. So E is a disk. So a disk here should appear to be just a circular structure. I'm going to draw in 3D. So that should be our disk. Okay. So given here, radius should be A. So that should be the radius of the disk. And the second information given, that our disk here have a density which is symbol-wise to be rho s and equal to Kr. So what been asked for us to determine now? Find total charge. Okay, that should be our objective. Okay, find the total, meaning that we have a structure, the structure have dimension, and then we have a parameter important for us to use, and then the question wants us to find the total charge. So first of all, when I want to solve this problem, I have to choose the appropriate coordinate system. So why? So that our problem will become simple. So we have 3 coordinate systems, which are Cartesian, cylindrical, and spherical. So which one should be the best coordinate system that we used in this particular problem? Okay, from the appearance itself, I would like to use cylindrical. Okay, so now our selected coordinate system for this particular problem is cylindrical coordinate. So now, what should be done next in order to make our problem simple? So I need to link the structure to our selected coordinate system, which is our cylindrical. So how do we make it simple? So to make it simple, I want this now to be located on the XY plane. Okay, XY plane. And then the axis of the disc is coinciding with our z-axis of the cylindrical coordinate. So that's how I make the link between the structure to our selected coordinate system in order to make our problem can be solved easily. Okay, so because the question does not mention how this should appear in the problem. So it's up to us. Therefore, this is what students must always see. The EMT problem seems difficult. Why? Because they always detach, okay, the problem with the proper coordinate system. Okay, they don't want to make it the decision themselves. They want everything should be mentioned. But in real engineering problem, we have to solve the problem based on our interpretation. So that's why we call it open-ended problem. Open-ended problem meaning that the solution solely based on our definition. We know the final objective of the problem, but the process of doing so is up to us to interpret. So what I did here, first I choose which coordinate system, which is cylindrical. Then I link the selected coordinate system to the problem itself by doing what? By making sure that this is located on the XY plane and the axis of the disc is coinciding with the Z-axis. Okay, inshallah after this everything will be easier. Okay, so how do we find the total charge? What symbol we give to our total charge? The symbol we give to our total charge is Q. Remember, in our discussion before, Q is our total charge. And then we know that it must be equal to the summation of all the sample appear to be taken from our source. So now the sample I'm going to draw to be on the diagram now. So how do I draw my sample? First, it must be general structure. So I'm going to make it just structure like this. Okay, that should be my sample. And the sample itself must always reside on the general position. I cannot choose my sample to be at the edge here. Because why? The sample must be representing a general position, must be anywhere on the disk. So therefore I draw it here because it looks nice. Okay, you can draw anywhere, provided it's on the disk. So this is my DQ. Okay, so now I'm going to introduce the parameter involved. So I'm going to define the position from the sample to the z-axis as what we define in cylindrical to be R. So that must be my R parameter. Okay, so therefore I know that where from our discussion before, the DQ here must be equal to, based on surface charge model, rho s ds. Okay, so then we have to substitute. Okay, rho s, no problem, because we know the parameter given already equal to kr. But how about ds here? Okay, ds must depend on the sample. So let's look at our sample now. So we can see the sample is located on the disk. Okay, and from that interpretation, we can conclude that the z is constant. Agreed? Anywhere on this particular disk, our z is equal to 0. Therefore, our sample is independent of z parameter. But yet, it depends on two other variables, which are the r and the angle. Because if I choose the sample to be here, the r is changing and the angle is changing. So how do we put that in terms of equation? Because we know the ds depend on the r variable and the phi variable. So therefore, in order to do that, we have to go back to our small box structure of the cylindrical coordinate, which we know consists of 6 different surfaces. So which particular surface from the box that we should choose to represent our ds here? Is it ds1? Is it ds2? Or is it ds3? Okay, so you have to go back to your box structure, and then from the box structure we can see that since this ds depend on the r and the phi, it should be taken from surface model number 3, which is RD phi. And we can see from this term, there's no z. So therefore, the z term we assume to be constant, as what we have seen before. Any point where the sample is located, the z always remain the same. So therefore, what we have to do now, we just need to substitute everything inside the total charge formula, where the Q here should be equal to, okay, Kr multiplied should be Kr squared dr d phi. And then should be how many integration involved here? 2 integration. And from the diagram, we know the limit for the r should be from where? From 0 up to a. And since our structure is complete circle, for the phi now should be from 0 to 2 pi. So that should be your substitution. Okay, so, and you can see it's not that difficult. Everything comes from the basic concept that we discussed before. Okay, that's one example that representing our third model of charge, which we know need to be a surface charge. Okay, let's do another problem here. Okay, so let's do another problem. So let's go back to the handout. So I see problem number 7 should be related to our volume charge. Okay, can we do that? Problem number 7. Okay, so let's read the problem together. Okay, a thick spherical shell. So the word spherical here indicate, so that should be the hint for me to utilize the third coordinate system, which is spherical coordinate system, centered at the origin, extend between r equal to 2 centimeter and r into 3 centimeter. We can see there's a unit given there, so we have to be particular now. So if the volume charge density is rho v, okay, that's symbol for our volume charge density that we known before, and then is not constant because there's r variable there, and then the unit now coulomb per meter cube. So we have now to relate this unit to our radius unit, so that make them consistent. So we have to convert the centimeter to meter. Find the total charge contained in the shell. So that should be what we have here, number 7. Okay, a shell. A shell should be a thick structure, meaning that not a ping pong ball. It's thick like this. Okay, so the center of the shell is coinciding with the origin. Okay, so we're going to make it linked to our XYZ axis that we know. Okay, origin. So the radius 1, the inner surface 2 centimeter, and then the outer surface here should be known as 3 centimeter. And then what given in the question, there's a volume charge. Okay, so the rho v now is equal to 3r times 10 to power of negative 4 centimeter per meter cube. So again, what the question asks us to do, very easy. So it's repeating now, find total charge. Of the structure. So therefore we know in terms of general definition, the Q must be the sum of the sample. So where is the sample now? Should be here. Okay, that should be our sample. Okay, so that should be our sample. So I'm going to make it to be known to be our dq. And then we know that the radius of our sample should be generalized. We know it should be r. And the sample should result from where to where? From 2 centimeter to 3 centimeter. And the sample also can have the other position. So it's also depend on the variable theta and the variable phi. Okay, so this can be seen from the simple diagram. Okay, since it's a volume charge, we know that dq from our model before should be equal rho v multiplied with dv. Okay, since we already decide this problem should be solved using spherical, therefore the dv can be substituted with the model that we've seen in the handout 2. In the table should be given as r square sine theta dr d theta d phi. Okay, because 3 variables involved in a volume. So now we can simply substitute now. So our Q should be equal to, so now triple integrations, 1, 2, 3. Why? Because the problem depends on the R, also depend on the theta, and also on the phi. Therefore, we need to have triple integration symbol to consider all the related variables. So now we just need to substitute. Okay, should be equal to 3 times 10 to power of negative 4. Then R with R now becoming R cubed. Yeah, R here multiplied with the R square is R cubed sine theta dr d theta d phi. So R from 2 centimeter, I'm going to change into meter now, okay, to 3 centimeter. Theta from 0 to pi. Why? Definition state that. Remember when we defined spherical, I did mention the range for theta should be from 0 to pi. And for the phi, should 0 to 2 pi. So you can make it easier by taking out the constant. So I'm going to first integrate the term of r cubed dr. And then I'm going to integrate the sine theta, d theta, and finally integrate the d phi. Okay, so now what you're going to have for this particular term, if you do it properly, so this will give us r over 4 over 4. So this will give us negative cos theta, and this will give us equal to phi. Okay, so with that, you can substitute the number into that particular solution of integration and you can get the final solutions. Okay, so that's examples. You can see by using the model to represent what type of source. Is it line charge? Is it surface charge? Is it volume charge? Use specific model. For example, here, volume charge, we're going to assume dq equal to rho v dv. Then from the model mathematics, we're going to relate to the diagram. And from diagram, we're going to link that to the proper coordinate system by utilizing the model that we have developed for our handout number 2. Okay, so if you do that properly, I'm sure EMT is going to be not that difficult. So now you can see. So you never memorize things, you never assume, you always make the clear decision. Okay, when you want to substitute something in our subject, must be reason why and based on proper concept. Okay, so I hope that you do other example yourself. Okay, in my next lecture, I'm going to continue with the Coulomb's law. So that's going to be in our next discussion. With that, thank you very much. Okay, see you again in our next session.